Hi everyone, my name is Bilal Aslan, and today I will be presenting our work, Paying the Price for Reach, which I co-authored with Geoff, Nitschke. In this research, we explore what happens when we take the abstract models of recurrent neural networks and ground them in a physical reality, forcing them to face with the same kinds of wiring codes that shape our biological brains. Let's start with the core problem we are tackling. In the natural world, brains aren't just software, they are physical organs. Every connection has a real metabolic and material cost. This wiring cost is a powerful evolutionary pressure that has profoundly shaped the efficient modular structure we see in biological brains. Now, contrast this with how we typically build our AI models. We treat them as abstract graphs, where any two nodes can connect with equal ease. By ignoring the physical constraints that make biological brains so effective, we potentially miss out on discovering fundamental principles of self-organization. What happens when you scale up network with wiring cost? Does a small constrained network organize itself in the same way as a large one? So to tackle that specific scale equation, we designed a study with these objectives. We started from that biological inspiration, the idea that wiring cost is key. We take an abstract graph, AI, and impose a physical cost. This allows us to answer our core question: what happens when we force an RNN to pay for its connections? And more specifically, how do performance structure and this cost performance trade-off change as the network itself gets bigger? To answer that question, we set three main objectives. First, we wanted to quantify the impact on performance. How do network size and the strength of its spatial wiring cost affect the network's ability to actually solve the task? Second, we needed to analyze the resulting structure. How does this cost penalty shape the network's final topology? We looked at key metrics from neuroscience like sparsity, modularity, and small worldness. And finally, we wanted to investigate scaling. Does the relationship between cost and structure stay the same as the network gets bigger, or are there size-dependent effects at play? To test this, we needed a task that was challenging enough to require sophisticated cognitive processing. So we developed a seasonal foraging task. We chose this task specifically because it demands multiple cognitive functions simultaneously. It requires working memory to remember the current season across a delay period. It requires long-term memory to learn the rules, which foods are safe to eat in which season, as you can see in the table on the right. And finally, it requires decision making to integrate these cues and choose an action. The trial structure is simple. The network is shown a season cue, then there's a delay with no input, where it has to hold that season in memory. And finally, it's shown a food cue and must make its decision, eat or don't eat. Our model is a RNN. The key manipulation is that we embed its neurons in a 3D grid, giving each one a physical coordinate and allowing us to calculate the distance between them. This spatial embedding is what allows us to introduce our wiring cost. Let's break this wiring cost down. The penalty for any given connection is proportional to its strength, its physical length, and its communicability, which is a measure of how important that connection is for global information flow throughout the entire network. This design discourages connections that are long, strong, and highly communicative all at once. It's a nuanced penalty. It allows the network to preserve essential long-range highways if they are functionally critical, even if they are costly. And on the right, you can see the key parameters we varied and held constant throughout our experiments. Results. What was the impact on performance? As you can see here, the good news is that all network sizes were capable of achieving high task accuracy well above 90%. This shows our model was effective. The key observation is how they react to the penalty. Larger networks, like the n equals 200, which is number of neurons, is, is the green line on the diagram, were much more sensitive. Their performance dropped more sharply as the wiring cost increased. Our interpretation is that larger networks with their greater capacity might initially learn solutions that rely on more costly long-range connections. This makes them more vulnerable when we start penalizing that specific strategy. Now let's look at what happened to the network's internal structure. First, as we increased the wiring cost, the networks became significantly sparser. The total weight of connection drops, meaning that network is pruning itself to become more efficient. But what's truly fascinating is that this pruning is not uniform. We found that few critical long-range connections persist even under very high penalties. This is our selective preservation finding. This intelligent pruning process is what drives the emergence of modularity. The network self-organizes into distinct functional clusters or communities, which you can see by the rising modularity score, especially for the larger networks. The takeaway here is powerful. The network isn't just blindly cutting costs, it's optimizing. It's protecting its vital long-distance highways while building efficient local neighborhoods. This combination of dense local clusters and a few long-range shortcuts leads directly to another hallmark of biological brains, small worldness. A small world network is one that perfectly balances local specialization with global integration. And we found that all our networks develop this property. As you can see, the small worldness coefficient, sigma, generally increases with the wiring cost. The interpretation is that penalty acts as a refinement process. It prunes away inefficient connections, shaping the network into a topology that is highly optimized for information flow, much like what we observe in nature. Putting this all together, we have uncovered a clear trade-off between task performance, the network size, and its structural efficiency. This trade-off reveals a sweet spot. At the moderate penalty level, around a lambda of 0.05 to 0.1, the networks produce the most brain-like properties, high modularity and high small worldness, without sacrificing their ability to perform the task. And critically, the sweet spot is not one size fits all. We found a clear scaling law. The optimal pressure is size dependent. Larger networks require a gentler penalty to achieve this ideal balance. The implication is that efficient organization in complex adaptive systems isn't a fixed target. It's a dynamic balance that is contingent on the system scale and the resource constraints it faces. In conclusion, our main takeaway is that imposing a single biological plausible wiring cost is enough to guide functional neural network to self-organize into an efficient brain-like structure. Our key contribution is demonstrating that optimal balance between cost, structure, and function is fundamentally size dependent. The broader impact of this work is twofold. First, it provides a computational model that helps us understand the principles that might govern brain organization. And second, it offers concrete design principles for developing more efficient and structured neuromorphic systems in the future. You can see an example of one of these evolved modular networks on the right side. Of course, this work opens up many exciting avenues for future research. We want to move from global cost to local competition. This is through a life approach where we model individual neurons as agents competing for limited resources. Can brain-like structure emerge from these local bottom-up rules? We can also explore embodiment or incorporate richer biological constraints, or we can test the scaling in modern large-scale architectures like LSTMs and transformers. Here are some references mentioned in the presentation. Thank you very much for your attention.
The evolution of the brain is a fascinating topic that has been widely studied, yet much remains to be understood. One big question is, why did some animals evolve larger brains than others? One theory, known as the cognitive buffer hypothesis, suggests that larger brains evolved to enhance survival in changing conditions. However, larger brains also come with higher energy demands, which isn't always feasible to sustain. Along with brain size, brain structure also plays an important role in cognitive abilities, and a better structured brain could be pivotal in addressing energy challenges that come with larger brains. Now here's the gap. The cognitive buffer hypothesis hasn't really been explored much using neuroevolution as an experimental tool, and most of the focus has been on brain size alone, not on how size and structure evolve together. This research aims to fill this gap. We investigate how changing environments and energy costs impact neural complexity evolution in terms of both size and structure. By evolving artificial neural networks within environments that range from static to highly seasonal, with and without imposing energy costs on network size, we can test whether the cognitive buffer hypothesis holds, the relative importance of size versus structure, and whether energy costs push evolution towards more efficient neural architectures. For our environment, we use a simple foraging task, where agents move around in a grid world, expending energy at every time step, and encounter two food types, denoted by grid cell color. One color is for edible foods, where if eaten, agents will gain energy, and the other color is for poisonous foods, where if eaten, the agents will lose energy. So these food colors never change in static environments, but in changing environments, the seasons shift, and with each season, the edible and poisonous food colors change too. So this means that agents have to figure out which color is safe to eat and which to avoid for each season. On the right, we have an example of a four-season environment, so we can see the agent moving around searching for food, with food colors changing with every season. The environment set used consists of four increasingly dynamic environments, where the first environment is static, as it only has one season over an episode, and environments become increasingly dynamic as the number of seasons over an episode increases. We also have two energy scenarios, the no energy cost scenario, where energy expenditure per time step is fixed, and the energy cost scenario, where energy expenditure scales with network size. We use reinforcement learning agents to solve the task, with learning guided by the PPO algorithm. Each agent has an actor and a critic feed-forward neural network, both sharing copies of the same hidden layer topology. This topology, along with the reinforcement learning hyperparameters, evolves over generations using the NEAT algorithm. For the neuroevolution process, we have a population of 150 genomes, each starting with a small fully connected feed-forward neural network with randomly initialized weights and reinforcement learning hyperparameters. Next, lifetime learning occurs, where reinforcement learning agents update their network weights over 1,000 episodes. After training, each agent's fitness is evaluated over 100 trials based on its remaining energy. We then select the top 10% of the fittest genomes to produce offspring via crossover and mutation, replacing the least fit 148 individuals. This process repeats for 400 generations. After that, we evaluate the neural complexity metrics of the fittest evolved genomes. So for the neural complexity metrics, network size, denoted as NS, is measured as the number of free parameters in the network, so the number of non-input nodes and connections. Network structure, denoted as NC, is measured as the balance between functional segregation and integration, which are two key components in brain organization. Segregation organizes information into specialized modules, while integration connects these modules, enabling communication between them. Neural complexity in this sense is considered low in networks that are either completely segregated or completely integrated, and high when there is a balance between them, which has been shown to support diverse cognitive functions. We measure segregation with modularity and integration with global efficiency. The balance is then computed as a ratio dividing the lower metric by the higher metric, where ratios close to 0 indicate low structural complexity and ratios close to 1 indicate high structural complexity. For our experiments, we evolved neural networks over 20 runs within 4 environments that increase in seasonality and under the 2 energy scenarios, one without and one with energy costs at scale with network size. First, we investigate how changing environments impact neural complexity evolution by evaluating the metrics for network size and structure that evolved across the environment set. This is done for both energy scenarios. Then, we compare how task performance and neural complexity metrics differ between the 2 energy scenarios to see whether imposing energy costs on network size drove evolution towards more efficient neural networks. Now on to results. For the impact of changing environments on neural complexity evolution, we first look at network size to test the cognitive buffer hypothesis. On the left, we have a box plot showing average network sizes taken from the fittest genomes evolved within each environment. In blue, we have the no energy cost scenario, and in orange, we have the energy cost scenario. On the right, we have a line plot showing how these average network sizes evolved over generations. The dotted lines are for the no energy cost scenario, and the solid lines are for the energy cost scenario. For the no energy cost scenario, where we look at the impact of changing environments alone, without considering energy constraints, across all environments, networks simply grew larger over evolutionary time, and no significant differences were found in evolved sizes between the environments. So the cognitive buffer hypothesis didn't hold in this case. So this actually mirrors findings from a study done on birds, where they found that larger brains evolved with equal likelihood in both stable and variable habitats. They even found that in some cases, larger brains could be more likely to evolve in stable habitats than variable ones. And that's exactly what we saw when we considered energy constraints that come with brain size. In the energy cost scenario, the more static environments, with only 1 or 2 seasons in them, evolved significantly larger networks than the 4-season environment, and a significant negative association was found between seasonality and network size, so more environmental change led to smaller networks, directly refuting the cognitive buffer hypothesis. Now this seems counterintuitive. Why would changing environments evolve smaller networks than static environments when the cognitive buffer hypothesis predicts the opposite? One explanation comes from the expensive brain hypothesis, which states that increasing brain size must be met by an increase in net energy intake or a trade-off with other vital organs. Now, since our setup has no competing energetic costs, it implies that to increase your brain size, you need to increase your net energy intake. Therefore, we looked at average task performance in terms of net energy intake, where we measured it as the amount of edible food eaten. And what we saw is that agents did significantly worse in the 4-season environment than the 1 and 2-season environments. And a mediation analysis confirmed that changing environments reduced network size indirectly by reducing task performance. So as seasonality increased, task performance decreased, meaning agents ate less food, reducing their net energy intake and making larger networks less sustainable. These results therefore support the expensive brain hypothesis and also align with empirical research on amphibians, eutherians, and marsupials, which similarly showed that increased environmental seasonality is associated with smaller brains due to energy limitations. Now we've looked at network size. What about network structure? So for structural complexity, we actually saw a similar pattern emerge, where for the no energy cost scenario, no significant differences in evolved structural complexity was found between the environments. And for the energy cost scenario, the 4-season environment evolved significantly lower structural complexity than the 1 and 2-season environments. And we found a clear negative relationship between seasonality and structural complexity. So very similar for what we saw for network size. However, if we compare how network size versus structure evolved over generations, we can see on the right that structural complexity increased over generations across all conditions, whereas this was not the case for network size. We can see this in particular in the 4-season energy cost case, shown as the pink lines, where if you look at the left plot, we see that network size initially grew, but then started to decrease after around 150 generations. Whereas if we look on the right, we see that structural complexity showed a moderate but significant upward trend across the full run. So across all conditions, structural complexity still increased with fitness, even in cases where network size did not. Finally, when we compared the two energy scenarios, we found that across all environments, imposing energy costs on network size consistently led to the evolution of smaller networks, yet task performance remained comparable. This shows that adding energy constraints can promote evolution towards more efficient neural architectures without sacrificing performance. Interestingly, imposing energy costs on network size didn't just reduce size, it also reduced structural complexity, suggesting a potential dependency between size and structure. So to further investigate this dependency, we ran additional evolutionary runs where fitness was assigned randomly, removing any task-driven pressures. Then, for every network size observed across these runs, we plotted the network's corresponding structural complexity. And on top of that, we plot the task-driven runs from our experiments in colour. And what we see is that the coloured points mostly overlap with the grey points, meaning the relationship between size and structure from the task-driven runs wasn't that different to the relationship that emerged purely from the mutation process. This suggests that structural complexity mainly emerged as a byproduct of evolving network size, rather than being strongly shaped by the task itself. This might be due to the evolutionary configuration we use, or to the limitations of using feed-forward neural networks only. So as next steps, we're testing alternative setups, including recurrent networks, to see whether structural complexity plays a more critical role in changing environments and energy-efficient solutions. In conclusion, our results showed that changing environments only impacted neural complexity evolution when energy costs were imposed. Under those conditions, more seasonal environments led to the evolution of smaller networks. This supports the expensive brain hypothesis over the cognitive buffer hypothesis, showing that organisms in fluctuating environments may actually evolve smaller, more energy-efficient brains. We also saw that structural complexity increased with fitness, but it was still reduced under energy constraints and changing environments, and likely emerged as a byproduct of evolving network size. At the same time, energy costs encouraged evolution towards more efficient neural architectures, which could inform the design of energy-constrained robotics. It is entirely possible that these results are specific to the current environment and evolutionary configuration we used, so for future work, we'll extend this to broader environments and alternative evolutionary setups. We also plan to explore varying the levels of energy costs to identify thresholds where they start to significantly impact performance, and also look into environments that have unpredictable changes to see whether they impact neural complexity evolution differently to the predictable seasonal shifts that we've tested so far. Another interesting investigation is to co-evolve agent bodies and brains to further explore the expensive brain hypothesis by seeing how agents balance energy allocation between their morphologies and neural architectures. Overall, the key takeaway is that energy costs aren't just a detail, they are a driving force in the evolution of neural complexity.
Okay, good evening, everybody. My name is Alessandro Scirè. I'm from University of Pavia, and thank you for inviting me here. The title of my talk is Portrait of a New Collective Intelligence, and it's based on the publication Emergence and Criticality in Spatiotemporal Synchronization, the Complementarity model. So, sorry. The problem I'm addressing is how does collective intelligence emerge from many simple interacting units? It's a big problem and it can be addressed in many ways. One, from the theoretical point of view, one possible choice is active matter. Active matter consists of dynamic agents that take in and dissipate energy. every agent is provided an amount of energy, and they used to deal with the interplay of positional and orientational order, and they display, in some cases, the emergence of large-scale self-organizing behavior. A typical example is the Vixek model for swarming. Another typical example, very famous, is active nematics for collective cellular motility. Okay, I had an idea. I created a new model for the interplay of positional and orientational order in active matter. The model first appeared in this publication a couple of years ago, and it deals with the collective dynamics of two subpopulations of polar agents that I call spins. And the picture is this: many spins moving and rotating in a two-dimensional plane. The degrees of freedom are the position and the orientational angle, and there is an interaction radius, so they interact up to a certain distance. The interaction scheme is this. I call it complementary interaction scheme because uh, if they belong to different families, they attract in space and push away in angle. So they attract in antiphase or antiferromagnetic coupling is also called. While where they belong to the same kind of, the same color, the kind of spin here is represented by different color. They repel in space and they try to align in the same direction. So the model consists of n coupled non-linear differential equation. This is the mathematical model. These are the degrees of freedom, their time evolution, and is loosely based on the Kuramoto model for phase synchronization, but then there are a lot of modification. I've introduced this function for the local forces, and these parameters gamma here is for saying if the one spin belongs to one family or to the other. Mathematical details can be found elsewhere. I'm going to skip all those details. And the main point is this parameter delta here, that is a form of circular anisotropy, is the control parameter. The effects of that parameter is there are a couple of effects. The first one is if delta is zero, the different spins tend to align like this. This means that they are attracted to the same position and align in antiphase. If delta is increased, this angle decreases, and if delta exceeds a certain threshold, the locking is the two spins unlock, so they go the separate way in space, and also they start to oscillate in opposite direction in orientation. So delta tends to make the red and blue spin rotate in opposite direction. Delta makes the system active, it provides energy to the system, and it creates local instability, both positional and orientational, when it overcomes a certain threshold. And we will see that it drives a global phase transition when I consider a many-body problem. Okay, for simulation, I used to start from a random initial condition in both space and orientation within a box, like this. And for small value of delta, this is what happens. They start to align in antiphase. Those of different kind align in antiphase like this. And they slowly pick up those one who left uncoupled like this one. Now the transient is a bit slow, I accelerate it a bit so you can see that the final configuration goes towards something like this. So there is translational invariance. They more or less put themselves in a regular array, and there is orientational symmetry breaking because they had to choose one specific but random direction, which would change if I repeat the simulation again. Delta also introduced a small dipole-dipole repulsive force that is what create this kind of regular array because each dipole is pushed to the border of the interaction radius. If I increase the anisotropy, still well the locking range, that is the threshold is delta equal to zero point 0.5. If I have delta equal to zero point 0.2, what happens is the following. I find a different kind of behavior, and I find specifically the formation of this kind of loops. These are counter-propagating loops of spin and transport current. You see, in the final situation is like this. They create a defect, a topological defect here, pointing at this point, and around this point is organized this loop. Okay, so I create a picture here. This is the topological defect, and this is the loop. If I leave those pin paint the trajectory like this, they would paint a ribbon like this one, a double helix structure. Okay, if I repeat the simulation, I find three cases. The symmetric, translational symmetric solution, this kind of vortex with this kind of defect, and also a vortex like this with the opposite kind of defect. This defect is aster, is like a star, and this defect is a spiral. But the center of the defect is always rounded by this vortex. Okay, those three solutions are very different. I mean, this symmetric solution can be predicted from local properties. It's just the local property here that is displaced and repeated in every lattice place. While this kind of solution is an emergent behavior, cannot be predicted from local properties, and in a collective arrangement of the flow of those currents. If I move delta a bit, I find different structures for even for the same values of delta, like those two here, the same parameters, but the ending situation is quite difficult. I see the appearance also of these stable patterns, and so there is a high variability in shapes, which is even for the same value of delta, which is a property that is called non-ergodicity. They sometimes happen in chaotic system like this one, in nonlinear system, and is a property that also happen in spin glasses or in protein folding. Those loops are persistent and are loops of frictionless current. They slide on top of the other without friction, something similar to what happens in superfluids. So I perform a statistic analysis versus the control parameter delta. I use time-dependent collective parameters, typical standard procedures in statistical physics, the translational kinetic energy, the rotational kinetic energy, and the Kuramoto order parameter for the collective synchronization. But this parameter, the kinetic energy, is the one that is able to reveal the presence of those loops. In fact, no kinetic energy are those points here that compete to the translational invariance regular static lattice of dipoles. And then there are many, many other solutions here, and those are the loops that appear until the locking threshold is overpassed, and dynamic solution, irregular, chaotic solutions start to appear. If I increase the system size, the scenario grows more complex. This will happen with 80 oscillator. With 200, I start to see the proliferation of those vortex, sort of vesicles that increase with the number of the oscillators until they form collective structure that start to be very complex, like this one. Now I show the movie concerning the regime situation of this simulation. That is something like this. You see that there are those currents, counter-propagating currents, both in spin, in orientation, and in position, that create this kind of loop of, I don't know how to call it, a complex of loops that expands far much uh, in longer distance respect to the interaction radius, and is also able to create dynamic states in the interior of those compartments. This is what can be classified as a collective intelligence, I mean, because represent the emergent ability of groups of interacting units to exhibit coordinated, adaptive behavior beyond the capacity of an individual part. Because I've also tried to add noise, to perturb, to break this structure, but it's able to recreate and self-repair to some extent. And it is also very robust if I add noise, for instance. That regime situation is found through three developmental phases. A first initial chaotic phase of self-optimization, where the system goes through many intermediate many intermediate phases, a sort of glassy self-optimization that the system passes through intermediate metastable states. A wide region of stabilization of the collective flow into this kind of structure, and then it can happen or not that it blows up all of a sudden, and I don't have yet understood what are the criteria for this to happen, and it's something that I'm still working on. The collective parameter time trace show reflect these three phases. In the glassy transient, they are turbulent with big jumps in all the collective parameter time traces, while in the homeostasis, the kinetic energy is more or less constant, the degree of synchronization fluctuates around the mean value, and the global frequency, this here, show peaks. This would be much smaller. This is amplified. Those peaks have power law statistics. There are many more details in the publication. This kind of thing reminds me is a form of liquid-liquid polymer condensation. Okay, in conclusion, I've introduced a new agential model, for the emergence and self-organization of complex synchronous spatiotemporal patterns. For bigger systems, those patterns proliferate into a complex network of frictionless currents that are robust to noise and that show long-range coherence. The pattern is something like this. Those patterns display complex statistical properties like glassiness, multifractality, and power law statistics. Uh, this is what I can call a new kind of collective intelligence. Those kind of patterns, I haven't seen them in any other kind of soft matter or active matter system. And I call it a collective intelligence because the control is decentralized, is a form of self-organization that spreads much over distances that are much wider than the interaction length. The rules on the local level are very simple, but the outcome is very complex. And there is a communication network that is this network. All the system is deterministic, so this a communication network based on a process of synchronization. That is what enable adaptation. And there is multi-scale competency architecture. There is no micromanaging necessary to uh, be sure that these kind of joints they sustain, they find itself by itself find the condition of the angle and the point in which on the length of the arms for sustaining a structure like this, which is already a small circulatory system. Those are characteristics that are observed in biology and explored in neural network and bio-inspired AI. This is why I think that this system is relevant for artificial life research. Okay, thank you. And this is more or less what I wanted to say. More details are included in this publication.